Okay, so similar to first order system, LCC ODE will summarize second order LCC ODE. So the general second order LCC ODE is y double dot plus 2 zeta omega n y dot plus omega n square y of t equal to omega n square u of t, where zeta is the damping ratio and it's a positive quantity, omega n is the natural frequency, um, and a mechanical equivalent of this is the mass spring damper system. So this is the governing equation, and electrical analog this would be a LCR circuit. So again we calculate the transfer function, which is similar to any LCC ODE. We take the coefficients, so omega n square by s square plus 2 zeta omega n plus omega n square, so we get the transfer function. Now to get the impulse response, we have to take the Laplace inverse of this, since the Laplace transform of impulse is 1. So yeah, so we have to break this into partial fractions, and to do that we need to find the roots of this equation. So again it's straightforward. We have the equation, we use the quadratic formula, and for practical purposes we keep the damping ratio between 0 and 1. So this quantity would be the would be a complex number, and hence we have now two complex roots. Now to get the constants a1 a2, we need to equate this to the overall term and get a1 a2. So now the impulse response is Laplace inverse of this, and this is the general equation. Now we just find the constants and substitute. So the impulse response has been combined, and this is this equation. If you remember, for first order it was 1 by t e to the power minus t by t. Now it's a decaying exponent, but multiplied with a sinusoid. So it is somewhat complex mathematical operation to compute some terms, but here we see that what t did for first order, here it's equivalent to 1 by zeta omega n. So we'll build on that further. So again step response is 1 by Laplace inverse. In S domain it's 1 by s times the transfer function, and again in time domain it's the Laplace inverse of this. So again we have the roots, we need to get these coefficients, and again following the similar methods we'll find the coefficients and substitute. So on simplification and combining all the terms, we get this. So again what capital T did for first order, it's 1 by zeta omega n for the second order system. So again for approximate calculations, we for example for calculating settling time, so we'll discuss what settling time is. So we see that the equivalent time constant for a second order system is generally approximated to be 1 by zeta omega n. So we'll build upon these factors in the next video, what is rise time, settling time, and overshoots, etc. in the next video. Thank you.